Hello, welcome back. In this lesson, we're going to see how to build GPIO driver using assembly language. So I'm going to create a new project by coming over here, new project, and then I'm storing it in this folder. I'll call this GPIO output. In this first lesson, we'll take a look at the output. And I'll select my board. It's the STM32 F411 VET. OK. I'll select over here and then I'll say OK. And the CMSIS, I'll select the core, and the device, I'll select the startup, and then OK. And then I'll come over here to target options. My Xstall is 16. Debug, I'll select the Stellaris ICDI. Over here, I'll come to settings. Oh, sorry. I should select the ST-Link debugger because this is the STM32 course. So the ST-Link debugger. Okay, so we select the Stellaris. We select the ST-Link debugger. I'll click settings here. Flash download. I'll click reset and run, and then OK, and then OK, and then target over here. STM32 board, and then I'm gonna click here, source group app, and then right click, add new item. I'm going to select S over here for assembly, and then I'll give it a name main. Right, so for those of you who have taken some of my other courses that relate to peripheral development, such as the bare metal courses, we already saw how to enable or configure peripherals for different boards, and some of you would already know how to do this in C language, and we know the basic steps. On modern day microcontroller, to enable peripheral or to use a peripheral, let's take our GPIO output as an example. We first need to enable clock access to the peripheral. Right, this is for all peripherals. Okay, and then dealing with GPIO, after we've enabled clock access to the GPIO port, we need to set the pin to output mode for this example, because we say we want to make it into a GPIO output. And once we've set it to output mode, then we can write to the pin. Right, so we need to enable clock, set a pin to output, and write to the pin. So before we go on, I'll just give a bit of history as to why these are the three compulsory steps. So for the first step, which says enable clock to peripheral, it's because of something known as clock gating mechanism. And what this means is that the clock access to each peripheral is gated. There is a gate there. You need to open the gate before clock is allowed to get to the peripheral. And this exists in modern day microcontrollers, regardless of the manufacturer or the architecture, whether you are using AVR, ARM, etc. All of them should have a bit of clock gating there. This is employed to help the microcontroller consume less power. And what this means is you only allow clock access to a peripheral when you need it. So over here, by default, all peripherals have no clock access. Because we're going to use the GPIO, we're going to use a particular GPIO actually, which is GPIO A. We allow clock access only to GPIO A, so that's the only part that the clock is connected. So that is why we need a step. And the second step, set pin to output. Okay, so any microcontroller at all, regardless of its architecture or manufacturer, when dealing with GPIO peripheral, you have at least two registers. You have the data register and the direction register. These two registers come with different names. For instance, the direction register in the STM32 documentation is given the name mode register. But in the Texas Instruments documentation, this register is called a direction register. and in some other microcontroller, their data sheet would give other names to the same register. And the direction register is used to set the GPIO either to an input or an output. And then the data register is where we write the data or read the data, depending on whether we've set that GPIO pin to an input or an output. So these are the three compulsory steps. Right. So what we have to do is find the addresses for these things. We've got to go to our reference manual and our data sheet, and then find the address for the GPIO peripheral that we are going to work on. We are going to be blinking the LED at PA5, meaning port A, pin number 5. So we need to first allow clock. Sorry about that. We need to first allow clock to port A, and then set PA5 to output, and then write output to PA5. And this corresponds to the same steps that we listed up here, and we have to do this in assembly. So for the Texas Instrument board, we have two important documents that we need. We need a data sheet and we need a reference manual, and then we can find those documents over here for the STM32, I should say. For the STM32 board, we have it here. If I mention Texas Instruments by mistake in this course, please do pardon me, because there's a Texas Instrument version of the same course. So you just click books here and you would find the books. We need the reference manual and the data sheet. Let's start off with the reference manual. No, let's start off with the data sheet. Okay, I'll click here. The reason we want to start here is we want to see the block diagram. We want to see the bus connections of the microcontroller. So I'm going to scroll down. There should be a block diagram somewhere. Okay, this is what I'm looking for. Okay, this block diagram shows us how things are connected internally to a microcontroller. How things are connected, how components, or I should rather say how peripherals or modules are connected to buses. So over here, if you look carefully, if you open yours and you look, we have AHB and APB, and we have AHB1, APB1, APB2, AHB2. In ARM architecture, there are two types of buses generally. For the ARM Cortex-M architecture, the Cortex-A and the Cortex-R may have other buses, but for Cortex-M, generally we have two bus architectures. We have the AHB and the APB. The APB stands for Advanced Peripheral Bus. The AHB stands for Advanced High Performance Bus. And the difference is the AHB is faster than the APB. The AHB allows for faster access compared to the APB. So if you take a look at what we have open over here, you realize that the maximum speed for APB is 50 megahertz. I'll zoom in a bit more. You find that over here it says 50 megahertz max, but if you take a look at AHB, it's 100 megahertz. So for instance, with APB, the peripherals are accessed slower. You cannot, go beyond 50 megahertz, and AHB allows that. So that's the difference. So we have to see where our module is connected, and as we can see over here, the GPIO A that we are looking for is connected to the AHB bus. AHB bus. So if we want to enable clock access for GPIO A, we've got to do it through the AHB1 bus, as you can see over here. If we start dealing with timers and we want to enable clock access to timer 2, we see this arrow connecting to APB1. So we would have to go through the APB bus. But for now, we're dealing with GPIO port A. So we enable the clock through through AHB1. That is point number 1. Right. So one other thing, or not one other thing, there are more things. The next thing is to find the address, the base address of GPIO A, because we have to know where it is in our microcontroller's memory so that we can write new data to that location in order to control the hardware the way we want to control it. So let's go to page 54 of the same document. I'll click over here, 54, hit enter. And this one here says register boundary addresses, and this gives the register addresses of all the parts, all the components, or I should say the peripherals and modules of our microcontroller board. It gives the boundary, the start address and the end address, and any peripheral you need, you can look over here. Over here it says the GPIO starts from 0x4002.000 and it ends here. This is GPIO A. So we take this as the GPIO base address because this is where it starts. So I'm gonna copy this. GPIO A base. I'll just put this here so that we can retype it later. This is just for taking notes. Right. So one other thing, in order to access the AHB that we just spoke about, we will need to access something known as the AHB1 enable register in order to be able to enable the clock access to port A. To do that, to have access to the AHB1 enable register, we have to go through the RCC. So I'm gonna get the RCC base address as well, and when we go to the data sheet we can read up on RCC. Right, when we go to the reference manual, I should say, this one is called the data sheet. It's got 149 pages. So over here I'll say RCC base. And for those of you who have seen the bare metal course, you realize as we write the addresses and the names, you realize that it follows the same order as the code we wrote in the bare metal course. And I'll explain what I mean by that. Yeah, I'll explain when we start seeing it look similar to actual C bare metal code. Okay, so we've got the base address for the RCC and the GPIO port A. Now, like I mentioned, these are 3 compulsory things that we have to do, and they all have registers that we access and modify. So in the STM32 language, the direction register is known as the mode register. So we need to find the address of this mode register. And then the data register is known as the ODR. There are 2 data registers in STM32. We have the ODR, which stands for Output Data Register, and we have the IDR, which stands for Input Data Register. We need the ODR, that's where we're going to write our output. And the way the addresses of these registers are arranged is that if you are dealing with GPIO port A, all the registers related to GPIO port A are an offset from this base address. So if we go to find the mode register is simply going to be an offset from this base address. If we go and we find the output data register of the same GPIO port A, that also is going to be an offset from this address. So it's just like adding a constant to this address gets us the address of the other registers, right? And you can think of this as, for those of you familiar with C data types, you can think of this as a structure with different members. You can think of the structure name as GPIO port A, and a member in the structure, the first member known as mode register, the second member known as output data register, and a whole list of members in the structure. And when you take this structure view, you know that the base address of the structure would correspond to the structure name, and then each member in the structure will be an offset from the base address. And yeah, that is the same way that it is arranged. Actually, I have another course known as object-oriented embedded systems programming, and we write the drivers from scratch using structures and using the same base member relationship. And we write the same code in C language, and then we write it in C++ as well. So for those of you interested in that, you can take a look at it. And in that course, we write the code that we write looks exactly the same as the type of code that you find in the, I would say, the manufacturer provided files. And what I mean by this is the type of code you find in the main.s and the main.c file that comes already made. Let's see what I can show you an example. Anyway, that's a different story, but let's focus on this. If you have any questions, just send me a message. I shouldn't divert, or I should stick to the point. So we have the base addresses. We have to go to the reference manual. I keep using the words interchangeably. It's because the STM32 guys decided to give different names to the document. If we are dealing with Texas Instrument, there's just one document known as the datasheet, and all information is in there. Over here we have reference manual and datasheet, and they have different informations. We've been taking a look at the datasheet. Now we're going to open the reference manual to get the particular register informations. So let's do that now. Okay, we open the reference manual by coming over here and then reference manual. So we said we have to enable clock access, and what we need in order to be able to do that is the AHP1 enable register. As we saw in the datasheet, our GPIO A is connected to AHP1. So we need to access the AHP1 enable register. You can search by doing Control F and then search AHP1 ENR, and then it will bring us here. You can just click to jump, and as you can see, the full name of the register is RCC_AHP. So that is why we got the base address of RCC from our datasheet. And over here you can see that it just gives the offset. It's giving the offset because it is telling us that its base address is RCC. So RCC address plus this plus 0x30 gets us the AHP1 enable register. So we simply need to copy this. And you can call it AHP1 ENR offset. Right. And let's read what it says over here. It says that the AHP1 is used to enable clock access. Does it say this? Let's see where this is written. Okay. Set and cleared by software. Okay, it doesn't say it's used to enable clock access here, but it should say it. That is what it is used for. It's used to enable AHP1. The AHP1 bus is used to enable that. I suppose the document thinks it is implied in its name that the name of the register tells us it should be used to enable the AHP1. So that's what it does. But what we're looking for is what the various bits represent. As you can see over here, bit 0 is called GPIO AEN, bit 1 is called GPIO BEN, bit 2 is called GPIO CEN. So let's go to bit number 0 and see what it means. You see the bits are listed here. I'm looking for bit number 0. So I can simply come over here, bit number 0, it's called GPIO EN, and it says IO port A clock enable, and it gives the meaning. It says if we set it to 0, then IO port A clock is disabled. If we set it to 1, then IO port A clock is enabled. So in order to enable port A clock, we've got to come to this register called this and then set bit number 0 to 1. So because of that, I'm going to create a constant in our code to help us do that. I'm going to say GPIO A underscore EN for enable, and I'm simply going to shift 1 to bit number 0. By writing this, what I'm doing is I'm taking a 32-bit number, which is 0000, 32 of them, and I'm saying put this number 1 at bit number 0. So it becomes something like this. Sorry about that. It becomes something like this. And this means we've got 31 other zeros, right? So this is what this line means. Okay. Right, so now we are done with the AHP. Let's go to the other registers that we need. We need the mode register. The mode is what is going to allow us to set PA5 to an output pin. We can find the information in the same reference manual. So come over here, and then I'll do a Control F, and then mode R. The R stands for register. I'll hit enter, and it brings me over here, and I'll click this. And over here you can see that we have mode 0, 1, 2, 3, 4, 5 all the way to mode number 15. The register size is 32. It's a 32-bit register, but we are able to configure the mode of only 15 pins. And why is this? Because each pin requires 2 bits. As you can see, mode 0 is for mode number 0 is configured using bit number 0 and 1. Mode number 1 is configured using bits number 2 and 3, and so on and so forth. And the reason why each pin, and you can think of mode number 0, mode number 1 representing pins. What it basically means, mode number 0 means pin 1 of the port. What it basically means, mode number 0 means is pin 0 of the port. Mode number 1 means pin 1 of the port. Mode number 2 means pin 2 of the port, etc. Whether you are dealing with port A, B, C, D, E, F, etc. So mode number 0 here corresponds to pin number 0 of whichever port you are working on. And the reason we need 2 bits is because we have 4 options. If we set both bits to 00, it means we are setting pin 1. If we are dealing with mode number 0 and we set bit number 0 and bit number 1 in this mode register to 00, it means we are setting pin 0 to output, to input, as it is said over here. If we set bit number 0 over here to 1 and bit number 1 to 0, as you can see over here, there is 1 0. It means we are setting pin number 0 to input, general purpose input. Right. If we are still configuring pin number 0, and this time if we set bit number 0 to 0 and bit number 1 to 1, it means we are setting pin 0 to its alternate function. And an alternate function is a function such as UART, PWM, DAC, etc. If we set both bit number 0 and bit number 1 to 1 and 1, as you can see over here, we are setting pin 0 to an analog pin, and this applies to all other modes here. And like I said, mode 15 should imply pin number 15, mode 10 should imply pin number 10, and they all have 2 bits. And these are the meanings based on how you apply the 2 bits. You configure the pin to a particular mode. Right, if you don't understand what I just said, just send me a message. So what we want to do is we want to set PA5 where our green LED on our nuclear board is connected. We want to set PA5 to output. So what it means is we want to set PA5. PA5 should be mode number 5, like I said, because I said the mode number represents the pin number. So we want to set mode number 5 to output, meaning we want to set mode number 5, meaning what we have to do is we have to set the 2 bits of mode number 5 to 1 and 0. So let's see mode number 5. Mode number 5 is over here. Where is it? Okay, this is mode number 5. Don't confuse the bit number with the mode number. This is mode 5. So mode 5 covers bit 10 and 11. So we have to set bit 10 to 1 and bit 11 to 0 in order to set pin 5, which is mode number 5 here, as output. So in other words, all we have to do is to set pin 5 to output. We have to just pass 1, the number 1, to bit number 10 over here, because the default state is well, this is the reset value of the register. I was about to say the default state is all bits are 0, but this is for other ports. But for port A, this is the reset state, meaning this is the default state. We have 0, 0, 0 everywhere, and then at the upper side we have this. So what we are concerned with is bit number 10. We simply need to pass 1 over here. If we pass 1 over here to bit number 10, we would have our pin 5 configured as output. So what I'm gonna do is create another symbolic name for us. To do that, I'm gonna call this mode 5 out. And like I said, if you have any questions along the way, just hit me up with a message. So mode 5 out, what I'm gonna do is I'm gonna shift the number 1 to position 10, bit number 10, and it follows the same explanation I gave you. I'm saying that we have a 32-bit number, and at position number 10 I want to place 1 over here. This is what is being shifted. This is the position, the shift amount, right? Maybe this doesn't correspond to 10, but I'm just using this as an example for those of you who count 1 2 3 4 5 6 7 8 9. Okay, I'll probably set it like this. So at position 10, and yeah, you have 32 zeros, and then you put 1 at position number 10. That is what this means essentially. And when we take this and we write it to our mode register, we're going to have PA5 set as an output pin for us. The next thing we have to take a look at is the next register we'll be interested in. That is the output data register. We can get the offset of that as well. And as you can see over here too, for mode register, the name is GPIO X _ mode register, and they've given just the offset here. The offset is 0x00. So I'll copy the offset. This is the offset, and the reason I'm pointing out the name is they've given just the offset because they know the base address is implied here. They are trying to tell us the base address is this bit. So whichever GPIO you are using, then the base address is for this, and then to get the full address of the mode register, you add the offset to that base address. So in our case, we're using GPIO A. The X here represents A, B, C, D, E, F, all the way to H as it's written here. So we're using GPIO A, and then we add 0x00 to the base address, and we get the full address of the mode register. Okay, once we've covered this, let's take a look at the output data register. It's called the ODR. So come over here and then click write. And output data register, this is where we write our output. So what we want is ODR5, because we are dealing with pin number 5. But before we take a look at ODR5, let's take our base address, our offset here. So this is the offset of this register. I'll copy this. And I'll put it here. Right. So because our LED is connected to PA5, when we write 1 here, when we write 1 here and our LED is connected here, the LED is going to be set on at position number 5. So what I'm going to do is I'm going to shift 1 to position 5, and I'm going to create a symbolic name to hold that for us. I'll say LED on. LED on, we're going to achieve LED on by shifting 1 to position 5 like this. Right. So now we have everything we need to start coding our assembly driver for the GPIO output. So this video is taking a bit long. How about we continue in the next lesson as we start writing the code to implement this?